session was to invite speakers from institutions elsewhere in India and from abroad to talk about their own work and research a little bit and their interest in brain science, and perhaps seed some collaborations. At least people get to see each other's faces and have conversations. So we first have I should say that we have 3 speakers in this session: Peter Littlewood, Vijay Lakshmi, Ravindranath, and Opinder. I would also actually, although he's not on the list here, I'd like to invite Professor Atsushi Iriki to chip in at the end with a few words about Japan, Japanese neuroscience perhaps. Don't have to get up and present slides, but just in the spirit of international collaborations. And of course, some of us live in the US or in Australia, so this is actually a pretty global crowd already, and the collaborations have started. I think I'm gonna go ahead and introduce Peter Littlewood. I think Peter is the reason I'm doing neuroscience today, because when he hired me at Bell, fresh out of graduate school, he asked me, and I was just, I was hired as a theoretical physicist, he asked me, what would I like to do? And I told him, well, I'd like to study the brain. And Peter said, great. Now I've never met another person who does such things, but I think his managerial strategy worked out okay. Actually, now Peter is getting interested in brain science as well, and so we have new opportunities to collaborate. So Peter, apart from having been at Bell Labs and headed the Department of Theoretical Physics Research, which had it was Department 11111. So the number 1 department times 5. He then went over to Cambridge and headed the Cavendish laboratory there, and he had actually trained in Cambridge as a bachelor's and a PhD student, so I guess he went back to his alma mater. But after 14 years at Cambridge, I guess he has returned to the US and is now the director of Argonne National Laboratory, one of the largest science and engineering research centers in the US, and he's also a professor at the University of Chicago. So, Peter, the floor is all yours.
Thank you very much, Partha. So, actually one of the great things about being at Bell Labs is, as a manager, you were allowed to say things like that, realizing that 20 or 30 years later it would come back to bite you. I think I need to tell you a couple of things. One is I sort of come here on a kind of a pitch for broad collective activity in the technology of doing neuroscience, which I'll talk about more, and I'll talk about the concept of a brain observatory. Probably not new to many of you people have talked about this. The other thing, of course, I should admit is that I'm not a neuroscientist. I mean, Partha is trying. We'll see. And that will become painfully obvious. But because of that, I come with a sort of set of conceptions which come from a physicist and about how physicists think about problems. And so I'll run through a few things. Firstly, let me just sort of give you some obligatory scale slides, okay, about where we are and why I think the technologies in a number of areas have advanced so much that there's a really unprecedented possibilities to do new things, actually. And these are all things, actually, which have happened since Partha decided to work on neuroscience and others. And I think many of them are underexploited. As an example of some of the things that actually do happen, this comes from a now colleague of mine, Bobby Kasturi, and this is a result of doing connectomics with serial electron microscopy. And so this is an area of the brain, there's about 1,000 cubic microns in there. But he decided just to take it apart and see what's actually there, which you can do in this. And so, whoops, oh, it doesn't do what I expected it to do. Maybe I need to click on something. Here we go. What you see in there, he sort of mapped all of the connections, all of the neurons going past. Some of them kind of slide past. Some of them make synaptic connections. You don't know in advance which is which. In order to be able to do that, you need to have something which you can study at a resolution of a few nanometers. Now, and this, of course, is a small piece of a brain. And the question comes to mind, if you're perverse, perhaps, and say, well, what happens if you wanted to look at a whole brain? Well, there's of this order of number of neurons and number of synapses, but kind of worse than that. These are manageable numbers. If you say, I just wanted to take a whole brain, study it at a 10 nanometer scale, which is the data level I need to take to discover whether something is connected to something else, it's fairly easy to work that is. It's 10 nanometers, it's 10 centimeters, it's 3 dimensions. So Google Brain Map, if you wanted one, is a zettabyte of data. So a zettabyte is 10 to the 21. We actually heard about zettabytes earlier today from Chris, and he pointed out that a zettabyte is a kind of a big number, but it's not an out-of-scale number. So 1 zettabyte is roughly the amount of data that travels over the internet in 1 year. So that's a very big number, but it's not. Well, actually, it is an astronomical number. So there are very few astronomical numbers that are bigger, but there are some. But it's not totally out of order to think about data sets which are on this scale, because a zettabyte is big now. Maybe in 10 years it won't look so big. Now, I mean, the thing which actually spun me up a little bit, actually, in the US, I wasn't going to put this up, but I decided I should, for the context of folks outside the US. A couple of years ago, what was announced was the BRAIN Initiative, which is an attempt to corral a whole set of researchers around technologies, technologies for doing brain science. And as always with these things, there's a sort of a burst of fanfare in the US where something is announced, and then the community looks up and says, well, what is this? And I think we spent the last 2 or 3 years trying to decide what we would mean by something like this. And I'm not sure that there's really a consensus yet. But I will say, that part of the reason for pushing this out was a sense that the scale of technologies that we have, the ability to take data, the kind of problems we want to look at, could be addressed in a very different way. So, to get down one level from that, what are some of us really proposing is I would say broadly, the idea of what I call a brain observatory, and I'll talk about a bit more, and I look forward to some discussion. One thing is really to try and maintain connectomics as a discipline. So, of course, this doesn't solve all problems. In fact, it may not solve any problem. I'm not sure what it's for. But it's one of those problems that feels to me that you should do it if it becomes possible. And if it's useful, one will build on it. There's beginning to be a real need, actually, for databases that will connect people's data, particularly multimodal data, particularly across scales and across functions, using different kinds of things. And the third one, which may be one of the most interesting, is a connection between researchers in engineering and physical sciences and biology and medicine. To broadly provide that kind of interface, because my observation has been in the US, that interface is very weakly connected, and there's a lot of opportunity to just introduce people across there to problems, so that the problems coming from neuroscience and from biology and medicine actually influence researchers in engineering and physical sciences, and in particular, they can develop tools. The tools could be mathematical tools, they could be physical tools, and to find a way of building that kind of community. Now, when one thinks about things which you call a brain observatory, one builds observatories these days which are global. It's a rather natural thing to do. It's not that this has to be something which lives in one place. But in particular, the national labs that I come from are a very good place to host pieces of this. So I should say something then about the national lab system in the US and what it does and why is it there. So there are actually 17, so DOE, is the Department of Energy in the United States. It's the equivalent of DAE here. And one of the things that the DOE does is that they run 17 national labs. There's rather a lot of them. Some of them do weapons-related things. One of them at least spends all of its time on what's called here environment. What that really means in the US is cleanup. The weapons program left stuff all over the place, which is very unpleasant. There are folks that are really focused around energy technologies, as is Argonne, but there are a bunch of labs that are really driven by science goals, 5 of them that are sort of multi-purpose, and then some of them that do one thing. Fermilab does particle physics, Princeton does plasma physics. But there are a group of us who have sort of missions to support broadly science in a range of areas which are related to the missions. Let's say, what does Argonne do? Argonne really does 3 things, and we're not so different in style, but we're different in detail from the other labs. Is that one is that we run user facilities for science. So we have a very large hard X-ray synchrotron, about which I'll talk more. We have very large computing. We have a nanoscience center. If you're a nuclear physicist, you'll know what that stands for. That's the Nuclear Physics Atlas rather than the Particle Physicist Atlas. These, it's worth knowing to everybody here because it's not widely known. When it's called a user facility, it actually means that it's free. If you want to come to one of these things or to use time on it, you just write a proposal globally. I mean, there's no preference for wherever you may come from. So it's just sort of peer-reviewed proposals to do that. We also do things that you might imagine for energy, like renewable technologies, and other things which are really related to energy and climate and sustainability, which is security. And security these days means environmental security as much as anything else. And supported by our own core science, much of which wouldn't be out of the way at a university. Okay. Now, where does neuroscience map onto this? Well, neuroscience maps onto this because we think we can help here, but also because it's very clear to us that neuroscience matters over here. The reason is that if you're interested in energy, you need to. We heard already this morning. We're about to get a 180 petaflop computer coming into Argonne. It'll consume 13 megawatts of power. Actually, it will consume more power than the X-ray synchrotron just to do computing. It's implausible that our computing is going to get much better because of the heat death that we're on with computing. So we actually care about low-power computing, and one of the things which drives the Department of Energy to think about this thing, about neuromorphic computing in particular, is the potential for just no power. The other thing, of course, is that over here we care deeply about distributed sensing and Internet of Things. And that also faces you with a set of problems which are systems problems for which the computing styles and the problems you need and the problems you want to solve are going to be very different from the ones where traditional architectures are there. Not just power, but the kind of problems you want to be able to solve. If you put a camera up on a street corner to support the city of Chicago, as we do, they'd like to know whether they're flooding or not. I mean, in Chennai, I guess you can tell when it floods. In Chicago, they don't always know. But then, there's a street camera which is taking a picture of the street. And the question that arises is, you don't want to beam back the whole image of the street, and probably you couldn't for security reasons, but you'd like to know whether there's a big puddle on it. So you need to have very efficient computation that can make a decision about whether I need to send a truck to fix a flood. And all of those questions are going to get embedded in problems, and that's just one of zillions of problems that come up with this. Okay. And actually, what does Argonne look like if you fly past it? It's a big place. We have deer, but we don't have monkeys. At least I don't think we have any monkeys. But the kind of things that are going on here, this is the X-ray synchrotron to put the scale in. This is 1.1 kilometers all of the way around. It's connected to a nanoscience center. This building houses computing, but there are lots of labs here for doing energy sciences. We have big programs in energy sciences. How many people work? There are 3,500 people who work at Argonne, about 1,500 PhDs. We have 300 postdocs. We're a great consumer of postdocs. We really like postdocs. We don't teach, but we do have students typically coming in on collaborative programs. So let me get back again to what are the kind of things that we are thinking about. I should say that nobody's committed to any of this. The amount of money I have to do this yet is quite small. But if you ask why the labs can help with the kind of class of problems that I'm talking about, it comes really because part of the things we're used to having very big tools. So simulation and curation, because we're the steward actually in the US of high performance computing and big data and thinking about classes of problems like that. We own big microscopes. So tools, and I say that the only two things I can think of which I can get resolution at the cellular and subcellular level is electron microscopy and X-ray imaging. And one would like to link this with all multimodal imaging technologies and also not to do it on things that are dead. But the nanoscience investments, as I say, there's a lot of investments in nanoscience over the years, and there's a lot of expertise and previous investment. And again, we're used to engaging in big projects and thinking in that way, and providing software engineers and software curation and data curation and running instruments. So this is the traditional reason that the DOE is involved in this kind of thing. So there's little bits and pieces of some of my own things that I'm keen on. When I first started hearing again about ideas about brain initiative and things like this, I said, why isn't anybody doing this with X-rays? So we tried, and actually it seems to be possible to do things with X-ray. So this is, of course, what you get if you look at a thin slice in electron microscopy imaging. This is the core of what you need to do that connectomics reconstruction coming from serial EM. And the way you do this, of course, is that you have a fixed brain and you slice it with a microtome. And then you image that, and here you can see that there's a synapse. And then you take slice after slice after slice after slice, and you have to have an algorithm that connects all of those slices together. And much of that algorithmics at the moment is done by high school kids, actually, because they're better at image recognition than we are. And as you see, this is all on the sub-1 micron scale. Go up to 5 microns, you begin to see things you look like. But actually, X-rays with the current generation of things, it's actually very easy to do things on a length scale which is about 2 orders of magnitude higher than this. One advantage you have with X-rays is that X-rays go through bulk, and I can use standard reconstructions to actually do a complete bulk reconstruction of a slice. So these slices are virtual slices, and this is actually taking more or less the same staining techniques and looking at that. And one advantage of this, of course, the resolution isn't so great, but this is actually about 10 minutes of data collection time for all of this, as opposed to the very complex and laborious process that you have to go through for that. And of course, using these two techniques together allows you to really aid in the reconstructions. Tomographic reconstructions parallels nicely. And so although while we may be concerned about the death of conventional computing, the computers we've got now are pretty good. And I can use so this is actually performance of a tomographic reconstruction algorithm showing that it scales perfectly almost with parallelization. And that one can do very fast reconstructions of big images. And now here's an interesting thing. So why use X-rays to do this? You're used, of course, to seeing X-rays in sort of dental imaging and things like that, where the purpose of using X-rays is to absorb the X-ray. If you go to hard X-rays, so this is energy up here above sort of keV. This is the penetration depth. So down here, X-rays get absorbed. Up here, they really don't get absorbed. The scale is 10 centimeters. They interact rather weakly with matter, which is very nice. So that means that they actually diffract. So that they're a bulk imaging tool. It's perhaps surprising to realize that you do much more damage with soft X-rays than you do with hard X-rays. The other thing is that it's element specific. So you can actually look at specific elements with X-ray fluorescence. And that means that you can actually have reporters because, it's quite easy to see fluorescence from a few atoms of calcium. A plug for the fact that this is where we are with the current. We're about to upgrade it. Actually, all of the hard X-ray rings, Spring 8, ESRF, will upgrade over the next few years to something which is much brighter. And with the photon flux, which is up here, we'll be able to do resolution. So this is actually data from current things. This is just imaging a zebrafish, just pointing out that you can actually see zinc, iron, copper. Of course, the resolution isn't terribly high on this, but we're already doing standard imaging techniques. We, of course, use it in material science. This is a grain of a battery material. You can see the stress on it. But by the time you get up to the next generation machines, this is a simulation, and we should be able to resolve a single vacancy. So single atom precisions. And in particular, dynamics. So this is the new generation of machines produce X-rays which are highly coherent. So they're like laser light. So that means that they produce a speckle pattern. So this is a simulation of a speckle pattern coming out of some imaging, and this is what it's actually imaging. Of course, these are all simulations, so one will be able to do dynamical imaging on timescales of microseconds, things like this. So some of the main questions that actually one has about this is not the difficulty about doing these experiments, but how long the thing that you've put in the beam will be living while it does that. The kind of thing that allows you to do is to do experiments rather like this one, which I sort of like. So this is optics. This is from a group in Europe. And actually, one of the reasons I put this slide up is it reminds me of something that Partha and I did a very long time ago, which is to do with holographic storage. So what this is that this is reconstructing a scattering image. And this is a real experiment, but this experiment has been done on a phantom. So what you have here is you have a ground glass screen in front of you, which of course you can, the light coming from a fluorescent object behind it is fluorescing and is emitting, is coming through the screen. But actually what you see, if you look at that, is just this. Can you find out what that image looks like from this? And the answer is because it's coherent, you can. And the way you do that is that, of course, so why are you getting this funny pattern here? You can see it's fluctuating. It's because the light which is going through here, which is illuminating this object, is illuminating it randomly. It's being illuminated by a speckle pattern. If you change the angle at which you shine light through here, the speckle pattern that's illuminating that object sweeps across it. And that gives you information from a correlation function which you can invert. And here's the actual object, and here's the retrieved object after doing that algorithm. Now, this is 2D. This is done with optics. And by the way, techniques like this, I think, could be used already, actually, in optical space on brains, because you need to have very strong wavefront control to get through deep layers and look for scattering. But I'd like to be able to do this with X-rays, to do real imaging. So the other kind of things that one has around, there's some examples of what people are already using in terms of nanoscience tools, is of course manipulating wavefronts for optics. So this is an awake mouse, which is being told to wiggle its whiskers at some point, illuminated by an SLM. And actually there are experiments done using two-color so that you can illuminate at one frequency and you can report at another. And what you need to be able to do is you need to be able to manipulate the wavefront here so that the wavefront accesses particular neurons with a particular scale. Nowadays, one has, as a result of nanotechnologies, micro-mirror arrays where you can do this with much higher precision. Typically, this at the moment is done through an SLM in free space. Now one can do this with nanomirrors, and that should get you megahertz repetition rates, and can actually have 1 million mirrors which are built on this to be able to produce very strong, interesting manipulations of wavefronts. And these technologies are just getting sort of pushed in to using that. So some of the things we actually happen to be doing at the moment, I talked about electron mapping. We're trying to do that. We'd like to actually eventually set this thing up as a user facility. Send it a fixed rate, we'll slice it, we'll send you back a piece. Developing the technologies for X-rays. To be able to do things which are live, of course, you want to be able to do multicolor microscopy. I pointed out that you can actually image elements. So calcium is actually very easy to see, but there's rather a lot of it, so it's a bit of a pain. But many of the things you could do, so we're beginning to work on looking at that. Simple things that come out if you start talking in the right place. You can actually have other kinds of reporters by energy consumption in neurons, so it's possible to have gold transported across membranes and find a way that it's activated by binding to ADP, so that you get gold clusters which are associated with energy consumption. We can do with this. Automated imaging reconstruction, lots of people are working on that. It's a real necessity for being able to do this. And then taking some of those MEMS things, and we now have a project at the moment which is actually putting miniaturized microscopes on the end of optical fibers which are very thin, and actually being able to feed them in through blood vessels, to be able to go very deep and actually to be able to locate them and then to be able to do imaging on this. And I say that we sort of got going on half a dozen projects like this very easily just by beginning to bring the right kind of community together. So my goal of this is, at this end, is to make more connections. So, I live in a lab which I say has got 1,500 PhD physical scientists. They know how to do lots of things. They don't know how to do neuroscience because they don't know anything about neuroscience. And we don't tell them to do neuroscience because they won't figure it out for themselves. They need neuroscience colleagues who will actually come and work with them and begin to develop the methods. But I think, sort of globally, however, I think we can reproduce this. We want a lot of connections to wherever we're going. And I've overstayed my welcome. This was actually the last slide.
We will have a little discussion afterwards, but if there are any quick questions for